go ahead and get started here. Everyone, thank you so much for attending the City of Cupertino's first virtual NASA speaker series starring Dr. Hwang. I just wanted to thank everyone for taking your lunchtime to be with us today. We think that this is going to be interesting, fascinating, exciting, all at the same time. And just want to let you know that due to the amount of attendees we have, we're currently about to hit, we just hit 200 people. We're not going to be opening up comments for oral comments. However, if you do have a question, there's a Q&A button on the bottom of your screen. So please go ahead and type your question in there. How this will go is that I will be passing this off to City Manager Deb Feng, who will say a few words. Then Dr. Hwang will give about a half-hour presentation, and then we will open up the rest of the time to Q&A with all of you. I don't see anyone who is on the phone, but if you are on a phone and you do want to ask a question, go ahead and email pio@cupertino.org. Again, that's pio@cupertino.org. And so without further ado, City Manager Deb Feng, would you like to take it?
Sure. Good morning, everybody. It's so weird to talk to people that aren't in the room with me, or I can't see their faces on the great screen of the Hollywood Squares. Let me introduce my good friend, Dr. Hwang, who is brilliant. She's a project manager in the Entry Systems Technology Division at NASA Ames Research Center, and will detail the trials and tribulations of the experience of the Mars Science Lab heat shield testing difficulties, and we'll also preview the next Mars mission, which uses the same redesigned heat shield material developed for the Mars Science Lab. And I know that everybody thinks it's interesting given our attendance. So I will not take up any more time and hand it over to Dr. Hwang.
Thank you so much, Deb. I'm really sorry that I can't be in the same room with you, and especially with everyone who is online. So again, I also want to say thank you for spending this hour with me. I really appreciate it. So let me try and share my screen. Oop, hang on just a sec. Sorry, this is not mean.
Is it not allowing you to? Oh,
no, it's just, yeah, here we
happening.
go.
Oh, there you go.
Yeah, we're just a little slow. That's okay. All is good. Okay. So hopefully, can you see my title page?
Yes.
Great. All right. Yes. So thank you so much for attending. And some of you might be wondering, who the heck am I anyway? And why are you listening to me? So I got my 3 degrees in electrical engineering of all fields from the University of Illinois at Urbana-Champaign. My background is not in space or aerospace engineering. My background is actually in simulating plasma physics for semiconductor processing applications. That's actually how I made it to the San Francisco Bay Area and how I actually came to work for NASA. And I've been at NASA Ames for over 20 years, kind of scary, but true. And I was the project manager for the Mars Science Laboratory, we call it MSL, the thermal protection system. And I have that same role again for Mars 2020, and I'll at the very end give you a little teaser about Mars 2020. And in my division, I am currently the Science Missions Development Manager, and what that means is I get to oversee all of the robotic missions that we do that involve atmospheric entry into a planet, and as well as proposals and whatnot. So it's a very exciting position. What I'd like to first do is give you a little introduction into what it is that I do and what we do in my division. So at the end of this, you'll be able to come out speaking just like a NASA engineer. And one of the important things about a NASA engineer is we love our acronyms. So the area of expertise that I'm talking about is entry, descent, and landing. So in NASA speak, we call that EDL. So we know that you're an insider if you reference EDL. And so these are 3 separate phases, which basically means from the time that the spacecraft hits the top of the atmosphere to the time that it makes a soft landing on the planet. that whole phase is called entry, descent, and landing. Those are three distinct phases. And what we do in my division is we concentrate on that first phase, which is the entry phase. And so any good EDL engineer, when they give a presentation, they have to give this little cartoon that we call ConOps, or a concept of operations. So that's our joke. We have to always have the ConOps in the presentation, and it basically tells you what's the sequence of steps that are employed in order to make that soft landing. And so what I put here in the green box, these are all the different phases within that entry interface. And that's what we really concentrate on, and we're really doing our best to make sure that that entry portion goes well. And so for the entry interface, the most important part is trying to slow down the vehicle. And we're bleeding off about 90% of the kinetic energy. And that kinetic energy then gets transformed into heat. And so that heat then will get dumped into the spacecraft. Well, we don't want that to happen. We don't want to cook our rover. That is not what we want to have happen. So we need to reject that heat. And how do we do that? Well, we use literally space age materials. And those materials then form the heat shield, which is basically, it's a passive device. We don't have to power anything on, but just through physics and chemistry, that heat shield material, it helps to protect that rover from all of that heating that's encountered during the entry phase into the Martian atmosphere. So I encourage all of you, JPL, they put together this fascinating video called The 7 Minutes of Terror. It's really entertaining. You should go check it out on YouTube. And so this deceleration, or the entry phase, that's the first 2 minutes of the 7 minutes of terror. So what we were trying to do for this MSL, the Mars Science Laboratory mission, was to land a rover on Mars, and it's still going there. It's still, chugging along, doing its science. It's wonderful. As you may know, this marks the third time that we have put a rover onto the surface of Mars. And here's a nice little picture that shows you the progression. So we started off with a very small shoebox size rover that's called Sojourner, and that was Pathfinder, the mission. Next, we put 2 landers in the form of Spirit and Opportunity. Those were the Mars exploration rovers. And finally, the one that I'm talking about, that mission, that's Curiosity. And so you can see that there's definitely a huge progression in size. The wheelbase width of Curiosity is about the size of an SUV. So it's quite considerable. It is a large vehicle that is being driven around the surface of Mars right now. Okay, so Curiosity, it got a ride to Mars inside what we call the spacecraft, or the entry vehicle. And entry vehicle, obviously, because it enters the atmosphere of Mars. So on the left, I have a cartoon of what that looks like. And then on the right, we have an actual photo of the actual vehicle that actually flew to Mars, not the people, but the vehicle itself went to Mars. And so when I talk about things, the heat shield, that's that sort of yellowish, brownish, khaki colored thing. That's the heat shield. That's the forward heat shield. And the white part, that's called the back shell. And inside of the entry vehicle, that's where we have the sky crane, which is also called the descent stage, and also the rover, which is all kind of tucked up. Its wheels are all tucked up inside. And so we usually use the terms entry vehicle and aeroshell somewhat interchangeably. So again, you're going to be speaking just like a real NASA engineer by the end of this. So this is what our entry vehicle looks like. And you can see on the photo, this is actually during the inspection process of the vehicle before it was sent off to Mars. And not that you can tell, but those 2 people, I know them very well. The one on the left is Robin Beck. She was our primary thermal protection engineer. And the one on the right, that's Pam Hoffman from JPL, and she was the overall spacecraft lead. So when we talk about the entry phase for Mars, we have to talk about in terms of magnitude of how hot is it. And so normally here on Earth, when we talk about how hot is it, we normally think about temperature. But when we talk about heat transfer, particularly for these materials, temperature is somewhat of an inexact way to describe just how much energy is getting deposited into this heat shield. So we like to talk in terms of heat flux. And so on the left, what I have, this very colorful picture, is actually some analysis that was done to predict actually how hot the temperature, surface temperature, is going to be on that heat shield. And so it's just sort of a top-down look if you were to look at the vehicle. And the very hottest portions are indicated in red, And so at that time, we were projecting somewhere around 225 or 250 watts per square centimeter. And it's really difficult to try to convey to people how hot that really is. What is 250 watts per square centimeter? So if you think about sunlight on your face, that's like 0.1 watts per square centimeter. A pretty heavy duty lab furnace, that's like 5. So this is many, many, many times hotter than what we normally experience anything here on Earth. So it makes it very challenging for us to be able to test these materials and to see, can they really perform in this type of environment? And part of the reason why it gets so hot is that this spacecraft for MSL was the largest that we had ever designed and actually sent to Mars to date. So it was considerably larger. It was 4.5 meters in diameter. So how do we test these materials? We test them in a facility that we have at NASA Ames, which is in Moffett Field in the Bay Area. And this was in a facility called an ArcJet facility. And we have some pictures here at the bottom. So on the bottom left, that's the actual facility itself. And you can tell by the pictures, it was actually built for the space shuttle. And most of the infrastructure that you're seeing are all of the water cooling hoses, because this is a 60 megawatt facility. I mean, this is a huge, honkin', incredibly energy intensive facility in order to recreate these types of heat fluxes that these materials will experience when the vehicle enters Mars. So it's a really large facility. We need to be able to cool it off because otherwise everything would melt. So we have a lot of water cooling hoses. That's most of what you see. But we do have the test section, and the close-up of that is seen in the bottom middle picture. And that's a sample that's undergoing testing, and the flow comes from left to right. So it's exiting the nozzle. And you can see all that, the bright material glowing because it's getting so hot. And then the pictures on the bottom that shows the before and after test. So that actually shows you what's, again, sort of what the materials look like before they actually get tested, and afterwards they get really nicely cooked and charred, so they're all black. All right, so when we were designing and developing this mission, and it takes a long time for a mission to come to fruition. So it takes somewhere on the order of like 8 to 10 years of planning to really get a mission ready to go and launch and be ready to enter Mars. So when we were designing this particular mission way back in November 2005, we knew that the heating was going to be very severe. We knew it'd be much higher than we've ever encountered before at Mars. And we thought, well, okay, it's going to be very hot, but surely the material that we've always used to go to Mars should be able to work. And this is a material that was developed by Martin Marietta, and they call it SLA 561V. So SLA stands for super lightweight ablator, because we use ablative properties. And the V stands for Viking. It was actually invented for Viking, the very first NASA missions to Mars. And we had used it very successfully for Viking, for Pathfinder, for the MER rovers, for Phoenix. We also, by the way, used it for InSight, which landed recently. And so this material has a high degree of flight heritage. We've flown it very many times. It's always worked wonderfully before. We thought, okay, well, we'll use it again for this particular mission. We know that, however, we're going to have significantly higher heating than we've ever encountered before. And so we know we have to do some additional testing because it really hasn't been tested to those limits before. In addition to the high heating, though, we also had some other phenomena that were going to be occurring. So we knew we were going to be encountering high shear force, so the flow that goes across the surface of the material, as well as before we had always predicted laminar flow in the boundary layer, which is a very orderly structured flow. But this time we knew we were going to have fully turbulent flow, which is, of course, as you can imagine, a very disordered, energetic flow across the surface. So we knew that this was going to be a first for a Mars mission. And at the same time, we were kind of keeping an equal eye to what the human exploration site was doing, because they were also looking to develop vehicles that they'll be flying, which are now actually called Artemis. At the time, they were called Orion. And so we thought, okay, we're better off partnering with them just to make sure that, they're testing some of these exact same materials. We better keep an eye on what it is that they're doing, because they also will be seeing some significantly high heat flux on their vehicle. So this is what, in September of 2006, we decided, okay, we better conduct some early tests of that SLA 561V and see what it looks like in turbulence. We actually had an ArcJet in at Ames that specializes in turbulent flow. It's called the turbulent flow duct. And the material itself is the right half portion. Ignore the left half portion. That's just sort of a spacer. And this is what it looked like afterwards. Now, you don't have to be a thermal protection system specialist to look at that and say, that looks kind of ugly. And that was our first response to all this. We thought, wow, I don't know what that looks like, but that looks ugly. And in fact, this kind of leads me, this is my personal opinion, I think that there is an unwritten requirement that all TPS needs to look pretty. And this definitely did not fit in that category. It really literally looked as if someone had dragged their fingers across this molten material, and there were rivulets of glass that had formed and cooled, and they were gouging, and it just looked really bad. We couldn't explain it. This was turbulent flow. It was higher conditions than we had tested this material to. It really just didn't look good. But we didn't know, what does this mean? Okay, it doesn't look good. We can't exactly explain why it looks the way it looks. But is that a failure? Does that mean the material won't work? We don't really know. So we needed to do some additional testing, some more analysis, and some more exploring. And in the meantime, we did a lot of hand wringing. And so we had to design a whole nother test series to say, okay, that didn't go so well. That didn't turn out the way we thought it would. We thought the material might melt and flow a little bit, but boy, that was not good. Okay, so but at this point in the project, we were gaining a lot of attention because if you don't have a heat shield that works, you don't have a mission that's going to land on Mars. So at this point, the NASA administrator himself was getting involved in the process, and that's a little bit uncomfortable for a mission to have someone at that high level paying close attention to what's going on with your little testing project at NASA Ames. So he was actually in attendance at the mission level critical design review. This is a major review and gate for the project, and he was actually in attendance and and he actually asked questions about the SLA 561V material, and he wanted to know how things were going. And at that, this is like a Hollywood script. At that exact moment, we were conducting tests at NASA Ames in the ArcJet facility on behalf of the Orion, now Artemis program, for this material, because we were both missions were interested in the performance of this material in these environments. And we were telling the NASA administrator and all the review board members, it's fine. We have this whole test program. We think we've got it all figured out. We've got this under control. Yes, we know we had some unexpected results, but we really think we've got the answer to all of this. We thought that we understood that, glass forms and this material at high temperatures, it starts to melt and flow. We can have this protective layer of melt layer on the surface. We think everything's going to be fine. It should be okay. So that was our story. And unbeknownst to us, meanwhile, back at the ranch, the testing was going on and the material was experiencing catastrophic failure, meaning it just blew apart. And this was also sort of a first for us. We had never seen a material behave in quite such a fashion. Some of the early tests, in fact, that were being done at these conditions, the material would literally disappear in a matter of seconds, like of the order of 4 seconds. That's bad. So as I said, very early on, the entry phase lasts for, on the order of two-ish minutes. So you need to be able to stick around for at least 2 minutes to protect the rover. So if the material disappears in 3 seconds, that means your mission has failed. That's not good. So this was back in September of 2007. So it's a whole year after we had those first kind of crazy results in the turbulent flow duct. So these are some still photographs from that actual test series that we saw some of these failures at. So you can see things seem to be okay, but then after 14 seconds you begin to see a little bit of a hole that forms, and then 16 seconds later what you're seeing are there's a whole bunch of holes that form. So what happens is this material is somehow being ejected out of the honeycomb that's holding it in. And then after 18 seconds, well, it's just going kablooey. So this is really not good. So we were changing the conditions, which is why this material went from looking okay prior to the 14 seconds. And then as we ramp up the conditions, it just blew apart. So it would lead to this cascading failure. It was sort of like a zipper. It would just zip, all pop out. And we just thought, oh my goodness, what is going on? We were scratching our heads, wringing our hands. We just thought, I just don't know. We'd never seen a failure like this before. So what do? We don't know. We don't know. So here is a video of that exact test series, and hopefully it's loading. So here we go. The flow is flowing from left to right. The model's inserted in the flow. It's flowing over the surface, and you can see all the glass rivulets are flowing along. Everything seems to be going well. Oh, bad. Okay, so this is the failure in real time, and that's really not good. So here we are. This is a video loop. So again, if you look at it, the glass flow layer is fine. You see some of these little poppings. That's some of the gases that are being released from the material popping through. That's okay, but that is not okay. Right there, that's the big failure. It's unzipping, and that means catastrophe. So that is a very, very bad thing. All right, so as I mentioned before, the heat shield, it has one job. And the one job is you got to stick around for the whole entry phase for the 2 minutes. Got to protect the rover. If you have holes in the heat shield, not going to be able to protect the rover. So very bad. We didn't know what to do. So what do we do? A lot of head scratching, a lot of hand wringing, not head wringing. That would be bad. So we did a lot more tests. We did a lot of new test configurations. We had this new test configuration called a swept cylinder, trying to mimic better the conditions that the material will actually experience upon entry into Mars. So on the left, you can see this is an actual photograph from one of those test series. And again, you can see all those vacant honeycomb cells where the material has just all popped out. And the very distressing part was this was actually at a heat flux condition that was actually lower than what we saw other failures at. So it's not like the heat flux was the only knob on this material failure. There had to be some other combination of events. Maybe it's a combination of heat flux and shear and turbulence and enthalpy. We don't know, but we know that this particular failure occurred in 3.4 seconds. So really, really not good. We tried to do some computational modeling to understand, were these environments, in fact, what we predicted they would be? Were they hotter than we thought they were? No, it turns out both the computations we did as well as the diagnostics we did, everything seemed to be right where we thought it should be, and yet we saw failures. So we knew in the meantime that we had to think about a backup option. And again, the human exploration side of the house, they were looking at a bunch of different materials. And one of their investments was in this material called Pika. And Pika was actually invented at NASA Ames, and it was flown on the robotic mission Stardust, which did a sample return of the comet's coma, and it brought it back to Earth. And so they were looking at a different configuration of Pika. So instead of a single piece of Pika, they were looking at a tiled configuration, sort of similar to like what the space shuttle did. So, smaller tiles that were glued together. And so we thought, okay, so, we did these tests of SLA. They turned out not to be good. So if you do a direct comparison of the exact same conditions, we tested Pika, and that's in the bottom picture. And it shows that Pika performs just fine. It does exactly what it's supposed to do. It gets charred, it turns black, but there's no failure and there's no anomalous behavior. Okay, so great to know Pika can survive these conditions just fine. It's a potential backup for us, but we're kind of still all in as far as SLA. Really want to make this work, really see if we can understand what caused all these failures. But in the meantime, we were still, okay, we need to try and test Pika and see how it does. In particular, we were concerned about the gap fillers. So again, if you're thinking about sort of like tiles on your bathroom floor, it's the grout part, right? The stuff that sticks all the tiles together. And we were concerned about, do we have a material that can work? And so we use this material, which is room temperature vulcanized. So we call it RTV. It's an adhesive silicone, and not too dissimilar from caulk. And so you can see that it's used to stick together the tiles. And so here again is an ArcJet test where we have some tiles that are stuck together with RTV. Again, the flow is from left to right, and you can see that the flow pattern is, in fact, you can even see it sort of forming on the surface of the Pika. You can see those sort of stripes that are forming, and everything seems to be just fine. It's performing. We don't see any failures. So this is good news. We seem to have a whole system, both the pica and the gap fillers seem to perform just fine. So we thought, okay, well, at least, we have an option. So, but now we're getting close. So it's T-minus 2 years to launch. We were originally supposed to launch MSL in November of 2009, and we have 2 years. We need to make a decision. So do we think that SLA is going to work, or are we going to have to do something else? So we thought, okay, we have two options. We can keep SLA, and we know SLA has worked really well on these previous missions. But we would then have to, in order to feel comfortable with SLA, we'd have to really severely limit what we think the aerothermal environments were going to be. So we'd have to make sure that SLA never gets close to actually melting at that glass melt limit. So if we did that, that means that we would have to really change the way in which we would enter Mars. And it's a very complicated business. There are a lot of things to consider, such as communications to Earth, how visible Mars is to the spacecraft and things like that, and where can we land. So these are all the things that we would have to juggle around in order to make sure that we could really limit the heat flux experienced by the heat shield. The other option is to switch materials of heat shield, knowing that we didn't have a lot of time, because 2 years seems like it's a long time, but actually in the world of spacecraft, that's really no time at all. So normally, as I said, it takes on the order of about 8 years to put together a mission. So trying to do a last minute switch with just 2 years until launch, that has never been done before. So we hemmed and hawed, we did a lot of hand wringing, and after examining all of the data, we really decided that, really we want to make sure that this mission is successful. Really the only thing we can do is we need to make sure that we have to switch materials, because we don't want to limit the science. Science is why we do this mission. We want to make sure that we have the full availability to go to all of the potential landing sites as possible. So we made that decision 2 years prior to launch that yes, we were going to switch materials. As I said, this has never been done before, and we were looking for a shortcut, and we got one, because as I said at the time, it was called Orion, now Artemis, the human exploration mission. They had been developing this material and gap filler system, so we decided, okay, now we're going to put all our eggs in the pica basket, and we're going to go full throttle on that. And so in order to make the schedule work, we said, okay, we're going to have to design and build at the same time, again, a method that we had never done before. And so one of the things we had to do was just test incredible amounts of pica and RTV and make sure that at a bunch of different heat fluxes and different conditions that it performed well. And we had to examine different things, such as on the top right, that's a repair plug. So, at some point, if somebody actually accidentally were to put a ding in the heat shield and later we needed to go back and repair it before it launched, that we could do that. And that looked fine. All of the gap fillers performed just fine. So what you see is just a bunch of charred blocks, and that's a really happy thing. So everything turned out well. You could perform just fine. All of our computational analysis was in line with what we had predicted. No signs of failure. The most important thing is it didn't blow up. So this was a very happy thing. So in March of 2008, we felt very comfortable that we had a whole system that would work for entry into Mars. So as I said, we did some analysis. I won't bore you with the details, but the most important thing is that we knew that this material was going to survive and it would protect the rover. So, with only 10 months from the time that we made that decision to switch materials, we did a heck of a lot of work, both analytically as well as experimentally. And here is the glamour shot of our heat shield. This is from Lockheed Martin. You can see that's a person. So this is, how large this heat shield is. It's 4.5 meters in diameter. This was built in plenty of time for the original launch of the MSL mission. And we were really proud of it. And you can see all the different tile configurations. Bonus, if you squint really hard, maybe you can find where we put some instrumentation. So bonus to you if you can find out where those instrumentation sites are. Very difficult to pick out. But much to our chagrin, unfortunately, we got a working heat shield that we knew was going to work for this mission. Unfortunately, there were other parts to this mission other than just the entry phase. And some of those things required a little bit longer development, such as the avionics, et cetera. So the very painful decision was made to delay the mission by 2 years. And the reason why is because of orbital mechanics. So we can't, if we don't meet the launch window, it means we have to wait another 2 years. So it's always a very painful decision to have to make if one is going to slip a launch for a planetary mission. Because unlike, for example, going to space station, which pretty much you can go at almost any time, the planets have to be in alignment, and that has to work out well. And so that only occurs about once every 2 years. So instead of 2009, we had a launch in 2011, but we knew we would have a heat shield that would work for that mission. So indeed, once MSL actually entered Mars in August of 2012, August 5th, we actually got, this is again the first time ever, this is an actual picture of the backside of our heat shield. You can see just the outer rim of that Pika, right? So this is the backside of the heat shield as it's being ejected, and it's falling to Mars. That all that red, that's the surface of Mars. So this picture made me so happy, and still makes me incredibly happy just to see that. So yes, so we were very excited. We had a complete success of the entire EDL sequence. So it was all worth it. So in the end, what is it that we learned from this multi-year hand-wringing exercise? I think one of the important lessons for me is that we really need to be careful about, we use the word heritage, and that is, we use it to make ourselves feel comfortable. Hey, we've already, used this material so many times before. It's been so successful. It's undergone a lot of testing, and the most important thing is we've flown it and it's worked. So we think heritage is a wonderful thing, but we have to be careful about how we think about heritage. And in technical speak, we always say heritage is only appropriate if you consider the operating environment, and it has to be in a relevant environment. And so what does relevant mean? And so a lot of people thought from the beginning of this whole experience that relevant meant Mars. But now we have a much richer understanding. It's not just Mars. It's, yes, because Mars of CO2 and the density and the variations of its atmosphere, but it's also how one enters Mars. How big is the vehicle? How fast are you coming in? All these things really combine to drive the environment into a different regime. And so we really have to carefully pay attention to that. And so Mars is not the relevant environment. The relevant environment, unfortunately, is many technical parameters that we have to consider. And so if we're not the exact same thing that we did before, that means we do need to do early testing. And so we were under a very compressed schedule because we did not do this early testing. And so I'd like to think that if we had actually investigated this maybe a little bit earlier, we would have been a little bit more armed. One can argue that it maybe wouldn't make a difference in the long run because the launch got delayed by other factors, but perhaps, some other resources could have been spent elsewhere. So who knows? But, again, I think it's important to think about all the factors when designing these particular types of missions. Don't be too complacent just because you think something has worked before. And I think most of all, I noticed from the technical team, they were very uneasy early in this design cycle, and they were very cautious about this material. They were very, very nervous. And me, as a relative newbie into this field, I thought that was interesting. They were quite nervous and twitchy, and I didn't know really what to make of that. And now I know better. So when your subject matter experts are getting very twitchy about things, it's best to kind of take a listen and understand, what are their concerns, and is there something that we can do to address those concerns? So that was all good and well. We had a very happy, successful mission. And so this is now the perfect time. We are now T-minus 1 month and 3 days to launching our next mission, which is actually very similar to the previous mission that I talked to you about. This mission, the mission itself, its name is rather Inglorious. It's called Mars 2020 because it's launching in 2020. But it has a lot of really interesting elements to it that make it new and different and special. So for the first time ever, we're going to fly a helicopter at Mars. This is a technical demonstration, so we have Ingenuity. So that's very exciting. We also have a new rover, Perseverance. We call it Percy for short. And that's going to do a whole bunch of mineralogy and chemistry on the surface of Mars at Jezero Crater. And I invite you to go look up at the NASA websites about all the exciting science that brings. And I'm going to talk just a little bit more about that. And then if you see at the bottom, boy, that sure looks familiar, doesn't it? Well, it should. It's what we call a build to print. So it's identical to its brother or sister or cousin that we flew for MSL. So the Mars 2020 entry spacecraft is exactly the same. It's a tiled heat shield for Pika on, and the back shell is the same too. And again, I invite you to squint very closely, and if you look, there's some little kind of stripy things on the edge of the rim of the heat shield, and that is for another discussion. That was our fun this time around. So the rover, Percy, I think one of the coolest things that it does is it's going to collect rock and soil samples, and then we're going to have a series of missions, and we're going to bring them back to Earth. That is going to be so cool. So it's going to do what it calls caching. So it puts those soil and rock samples into these little cylinders, and it's going to collect them. And then we're eventually going to send another mission to Mars to go pick them up with a fetch rover. And that fetch rover is going to be supplied by the European Space Agency. So this is going to be a really exciting set of missions. So, and then we're going to launch those samples back into orbit around Mars, using what we call the Mars Ascent Vehicle, the MAV, M-A-V. And then those samples are going to orbit around Mars, and then we're going to have some other spacecraft come and fetch those samples and sterilize the whole container, and then bring them back to Earth. And if you see the picture on the bottom right, I've outlined in a little dashed oval. That's the Earth return, the Earth entry vehicle, the EEV, and that's going to come back to Earth, and it's going to bring those samples back to Earth, which I think is going to be amazing. That's going to be the first time that we will have samples from another planet back at Earth for the scientists to really examine and run all kinds of wonderful experiments on, and we're going to find all kinds of new things. So I'm very excited about that. These sets of missions, they're all in the planning stage, but it promises to be a very exciting time. So in closing, I really just want to thank everyone who's listed on this page and then some. These are all the people who worked really hard on this whole story that I told you about. I get all the fun. I get to talk to everybody and answer questions and interact with the public. But these are the people who did all of the really difficult work. They did the analysis, they did the testing, and the building. And so thank you, everyone. It really takes a village to build a heat shield. So thank you so much. And I'm very happy to answer any of your questions. I hope you found this to be interesting and entertaining as well. So thank you so much for your time.
Oh my gosh, Helen, that was amazing. I like the Hello Kitty vehicle though, the best.
We're working on that.
Looks like we have a lot of questions come up, Brian.
Yes, we do. So first of all, thank you, Doctor. And we have had quite a few people thanking you throughout your presentation. They called it exciting, so that's good. Hopefully Jacob White, who asked this question quite a while ago, is still on. He said, why do the peak heating and peak deceleration happen at different times?
Yeah, so very good question. We can get into, I think, a lot of good physics discussion about that. But basically, peak heating has to do with the momentum transfer of the atoms that are interacting with the spacecraft, and also the shock distance of the gas and the standoff distance from that. So a lot of that just has to do with that sort of physical interaction with the vehicle. The peak G's is a function of how fast basically the spacecraft is falling. So that you wouldn't necessarily expect to have those align at the same time.
This isn't really exactly what you're talking about. But we had quite a few people say, when are we getting people to Mars and other kinds of planets and things?
Yeah, great question. Love this question. Yeah, I would love to know myself. So it is going to be a great technological challenge to send people to Mars. I'm up for it. I think it's going to be really exciting. I really think that that's going to be, in addition to this whole Mars sample return set of missions, that's really going to be the next giant thing. And I think that's going to be so exciting. There are so many technology developments that are required for that to occur. And actually, in my opinion, I'm an engineer. I think actually the technology is the easy part. Not that I have answers, because I definitely don't have answers. But I think we have a bunch of really smart, hardworking people, and we can get answers. Given enough time, we can get the answers. I think what's really challenging and what makes it so interesting to me is the human element. And that as of right now, the only way we have to get to Mars is chemical propulsion. So it takes about 9 months, about the same time that it takes to, have a baby. So it takes about 9 months to go to Mars, and then it'll take 9 months to get back. And as I said, you have to have orbital mechanics work for you. So the planets have to be in alignment. So either the astronauts stay there for 2 weeks, which is not good, or they have to stay there for 2 years, which is more likely. So they have to be able to stay there for a long time. So in order for humans to actually be able to survive in that long duration to Mars and back, and also to stay on the surface of Mars, requires a lot, not just from technology, but I think a lot of it is psychological. And I think what's been so fascinating to me is to watch this whole COVID thing, and about how do humans respond to being in isolation. And we don't respond well. And it's hard. It's really a strain on us mentally, spiritually, physically. So I think we have to learn a lot about how do we cope better, because that's going to be a long time for people to be in isolation. And that's what I think is the biggest challenge. Like I said, the technology, you find the right smart people, you can figure that out. But this is really, how do you crack this? How do you get people to be okay in isolation for long duration? I don't know.
Hey, Helen, I don't want to interrupt too much, but I wanted to ask your expertise to connect it to the Artemis program, right? The program to send humans back to the surface of the moon, and perhaps the gateway that's related, and the ability to sustain life, create new fuels in order to use the moon as a jumping off point to Mars. And maybe that, right?
I think, those are great ideas. And certainly, I think that helps a lot, right? Having the moon or the gateway as a base, I think helps dramatically. And certainly it's a less isolating experience because they're much closer to Earth. I think that's a fantastic idea. But the part that still concerns me is the part that going out to Mars. We still haven't figured out a short way to do that. So the only way to do that is to advance propellants, or advance really, this whole idea of propulsion. How do we do something other than chemical propulsion? So for me, I still think the biggest challenge. I think also one of the things we learned about during this MSL mission, because we measured the amount of radiation that the interior of the spacecraft experiences during that what we call cruise to Mars, while you're traveling to Mars, is much higher than we had originally anticipated. And so that's also a problem, because obviously we don't want to be irradiating our astronauts. That's not good.
So this question is really both for the doctor and Deb. We had an early question that asks, how do you get to work for NASA?
Well, yours might have been a little more purposeful, Helen, so why don't you go ahead?
So I had a very circular path, torturous path to get where I am. As I said, I had my degrees in electrical engineering, not aerospace engineering. And I concentrated on semiconductor physics. I actually got a job as a contractor at NASA Ames originally, and I was working in the research and development area of semiconductor processing. This was so long ago that back then the high-tech term for it was microelectronics. And now, of course, nanoelectronics and smaller than that. But yes, but back then, micro. So that's what I was working on. I did not work on anything space related. I was working in the same building as the space guys, and I became friends with them. I thought, hey, that's kind of interesting. That's kind of fun. When our nanoelectronics money ran out, which happens in any organization, funding pots dry up. I was looking for something else to do, and they tempted me, and they said, hey, we have this really interesting little project called MSL. Would you be interested? And me not knowing any better said, sure. So that's kind of how I fell into it. It's actually very technically related in a way to what I had done before. It's this gas surface interaction. You have to know a lot about materials, and you have to know a lot about sort of chemical engineering and applied physics. So it was sort of a happy coincidence. So that's kind of how I came to NASA. Deb, I'm sure you had an interesting journey.
It's strange. I have an undergraduate degree from Berkeley in mass communications, radio, and television with a minor in psychology, which is weird. And then I have an MBA from San Jose State, which is a general MBA. However, my path was really literally a wrong turn on the wrong off ramp. So I was heading up to Menlo Park for an interview as a technical editor. And I made a left turn, ended up at the main gate of NASA Ames, which having grown up in Cupertino, I had no idea it was there my whole life. Who knew? So this is one of my things about bringing NASA to Cupertino, because I feel like we're just that distant. At least back then, we didn't have kind of the whole internship robustness and the programs we have. I wanted to bring it to Cupertino to ignite like the next generation, right? We need replacement units to come in. Anyway, in my line of work, I ended up being the Associate Center Director at NASA Ames, basically operations. So like a little city, that's what I was responsible for, which I think is how, in part, I got this job. So a strange, circuitous kind of process in my career. Probably one of the most interesting points was when I ended up being the division chief for our spaceflight hardware manufacturing division. But there's a whole bunch of jobs at NASA and NASA Ames that are in support of cool researchers like Dr. Hwang. They need communications people. They need people who can do IT. They need people who can manage the money. They need people who can manage facilities, do construction, do maintenance, landscaping, any kind of business function that you can think of. NASA Ames needs it too. And so I invite people, if you're interested in the space program and, you're not big on math, or you have a communications bent, or you have some sort of other interest bent. I started as a secretary, believe it or not, and that job I was able to learn a lot about process, which is what drives all of the business, both at NASA and other organizations. So it's pretty cool.
Yeah, I agree, Deb. I mean, we need all kinds of people to do all kinds of functions. I think in general advice is study hard, be great at what you do, and be enthusiastic, and see what's open. Right? We have NASA jobs, so go check out that website. And you just never know where your life path leads you. So I think Deb and I are both testament to that, right? You just never know.
You don't know. Just remain open. Everybody thinks you have this big career plan. I did not have a big career plan.
Yeah, I didn't either.
This is a little off the wall. Do you know Mark Rober?
No.
Okay.
I don't.
He's a YouTuber who does a bunch of science things. So someone asked that. Getting back to actually what you were working on, folks wanted, if you could just quickly go back over it. What was the material made of, and how does the material burn?
So those are great questions. So SLA 561V is kind of this hodgepodge of materials. So the Honeycomb material is made out of fiberglass, and the resin inside is made out of a bunch of things. So there are things like cork, there's some silicone, there's some glass microballoons, there's some silica microballoons. So there are a lot of things to try and keep it very lightweight. So again, remember, it's called super lightweight, right? So that's the whole thing about SLA. Pika is a little bit different. It's a very lightweight version of carbon phenolic. Carbon phenolic is a material that's actually flown on ICBMs. But this is a whole different way of envisioning it. So it's these light, fluffy phenolic and carbon fibers that are made. And actually the basis of it is this thing called fiberform, which was actually, it's used in commercial processes, like for insulation for like these types of either thermal ovens or things like that. So it starts its life as that, and then we do a lot of specific processes for NASA reasons, and we can turn it into Pika. So it's these materials are made out of a whole bunch of types of constituents. Most of them tend to be carbon-based, because we found that carbon does a great job of re-radiating that heat back out into space. So again, the whole heat rejection that we're trying to perform.
And we just got one question to kind of follow up on that. Has the Pica material been used for anything else?
So Pica, as I said, the first time we used it was actually for Stardust. So that was a successful mission. We used it for MSL. We're using it again for Mars 2020. And we actually did a technology transfer to SpaceX. So their material is called Pica X. It's based on this Pica technology. So yeah, it's specific for these types of entry vehicles. It's a very specialized material. It's not really meant to be for every day. I'm going to put my use it as a coaster or something like that. It's really meant for these spacecraft.
Right. And this was a very early question on why is argon used?
Yeah, so we use argon as a buffer gas in the test facilities. It helps with the gas flow for the ArcJet facilities. It helps with the mixing sometimes to help the flow that comes out of the nozzle be a little bit more uniform. So typically we want to use an inert gas that we know is not going to cause more chemical reactions and then cause a very confusing sort of mix of reactions that happens on our test particles. So we want to have a gas that we know is going to be non-reactive. So unlike oxygen, which is highly reactive. So we want to use argon.
Great. And you brought it up, and we've had a few questions that kind of revolve around this. How much partnership is there between NASA and SpaceX?
Oh, great question. Yes, there's a lot of partnerships. So hopefully that's something that people are learning about this recent space launch, which, by the way, is super cool. So yes, we have these commercial crew contracts. We actually contracted with SpaceX and with Boeing to actually make these rockets and vehicles to charter our astronauts to and from space station. So we work with them very closely. We are very excited to have our commercial partners. So yes, we do a lot of partnership with them.
And that I would just add that last launch was historic because it's the first launch from U.S. soil with a U.S. vehicle since 2011, since the retirement of the shuttle program. And it's significant because the way that our astronauts were getting to the space station was on Soyuz, which is a Russian vehicle. So that's good and bad in that one is you can see that space and space research is very collaborative between interesting governments who otherwise wouldn't get along. But the science really kind of cuts through all of those politics. And so what would happen is our astronauts would have to go to Kazakhstan, get ready for a launch and launch from Russia. So it was historic in a number of ways, not only for SpaceX, but for NASA and America to be back on the station from U.S. soil. It was a big deal.
Yeah, it really was, and great achievement by SpaceX. So we're so thrilled.
So we just still have a few minutes here, and we had some questions very early on. They may have been answered already, but I didn't want to go over them because these folks are still on the line. This one is to clarify: the honeycomb is not the material itself. It was structural element left behind because the material was popped out? Was the question.
Interesting. Yes. So this is actually, when I first started out too, I was a little confused because we have all different kinds of honeycomb. So on the back side of what we call the TPS, the thermal protection system, there's aluminum honeycomb, which is actually the structural part of the spacecraft itself. The fiberform honeycomb, it gives structure to the heat shield material. But it's not a structural material in and of itself. It's not meant to be load bearing or anything like that. It basically it's sort of giving you a form to basically squeeze the resin into. So it holds all of that resin in its cells. And it was left there simply because we think because something about the process of when the material got heated up and some of these ablation gases would form and then eject the material out. That's sort of our leading theory. We still haven't really solved that issue, by the way. So if you guys have good thoughts, let me know. But that's what was left. So the honeycomb itself does actually ablate and melt as well. It's just that in this particular failure mode, the honeycomb itself didn't appear to fail. It was just the resin, for some reason, seemed to just fly outside of the honeycomb, and we don't know why. Very weird.
All right, we just have a couple of minutes here, but we do have a lot of questions we're just not going to get to. Just in general, where would people go to find more information about what you're working on, and maybe anything else you think might be of interest to this audience?
Great question. I should know the answer to this. Maybe Deb does. I would go to nasa.gov. And from there, you should be able to access Ames Research Center. You should be able to look at all the NASA centers and see what we do. I know the Entry Vehicles and Technology Division, which is where I work at NASA Ames, we have a webpage within Ames. So definitely you can work on that. Look for that. You can just do the good old-fashioned brute force Google search, which is what I tend to do. So, you can try Googling NASA Ames entry systems, and hopefully things can pop up there too. Or if you're interested in the missions, look for Mars Science Laboratory.
Yeah, that's where I would go. The other thing that I would suggest is for those that, were not able to ask their questions or kind of came in the middle, there is a video that Dr. Hwang referred to, 7 Minutes of Terror. And we joke at Ames that if there was a failure in the first 6 minutes, it would have been on Ames. The last minute was JPL, Jet Propulsion Laboratory at Pasadena. But we will attempt to post that link to our website for the NASA Speaker Series that highlights Dr. Helen Hwang. It has been recorded to answer some of the questions in the chat. And so you can view those. And if we actually were at work, Helen, you would be playing, your speech would be playing in a loop in the lobby so that people could watch it. But we can have the video posted so people can get to it. And I believe the first 2 speakers were also videotaped and posted on our website. It's been very popular, which is cool.
Yeah, so for everyone, oh, sorry.
Sorry, no, I just want to say I'm really sorry that I'm not there in person. Usually what I like to do is I like to hang around for as long as it takes to answer everybody's questions, because I know people are very enthusiastic and I love talking to people. So I'm just really sorry that, we can't all be in person together.
And for those of you who are going to want to rewatch this, we will have this uploaded to Cupertino.org/YouTube. So again, Cupertino.org/YouTube. That will take you straight to our YouTube page, and it should be uploaded very soon. So I want to thank all the attendees for coming, and I'm so sorry for those of you who did not get your questions answered. I do hope that you enjoyed the presentation. Deb, Doctor, thank you so much for attending.
Thank you so much, everyone. This was so much fun.
Thank you, Helen. So appreciate you doing this and seeing you.
Thanks for inviting me. So good to see you.
Take care, everyone.